Validate a binary search tree. Given the root of a binary tree, determine if it is a valid binary search tree. A valid binary search tree is as follows. The left subtree of the node contains only nodes with keys less than the node's key. The right subtree contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. So the problem description sounds pretty straightforward. So let's think through this. It's a tree, so automatically you should be thinking recursion. And indeed, we are going to use some recursion. Now let's talk about kind of a target runtime and space complexity. We're probably looking at as a tree, so a depth first search kind of recursive deal. That would give us, we have to scan the whole tree, so a minimum of linear time. And we probably don't need to do worse than that. I think we only need to look at everything the once. The other thing to note is, okay, normally for these kinds of problems, I would recommend making a separate function that does most of the work, and all this main function does is kick it off. It sets up the arguments and it makes a call. In this particular problem, it's actually, I think, it's reasonable to just use the one function and then have, the final solution be the return of the top level call. And now let's deal with space complexity. It's probably gonna be linear space. It's a binary search tree. Suppose it would be kind of weird, but I guess possible if the tree is still like a big line where maybe you have only left children, say, oh, it goes all the way down to the left, and the root is the largest item, then every item to its left is going to be smaller, and then it keeps going down and down and down, and that would still be a valid binary search tree. So that kind of weird input, you could get a linear space complexity because you end up with every item on the stack frame. And I don't think you can do less than that because you do need to build up the solutions. To know if a particular node is valid, you need to know if its children are valid. Meaning you're either going to have to save some of that information in stack frames or, well, actually, I was thinking maybe if you do dynamic programming type of thing where you have like an array instead. But actually, okay, so suppose if you knew the structure of the tree and you went, all the way, was there a drawing function on this? I wish there was a drawing function on these kinds of things. Editor, shortcuts. If you've ever done like a CoderPad submission, those usually have some kind of drawing. Hey, bingo, here we go. This looks promising. Nope, never mind. Anyway, so if all you need to know is the immediate children and you kind of knew the layout of the tree, you could go down to the leaves first and then get the information for that. And then you could collapse that information. If you've ever dealt with parallel algorithms on trees, that would be called a compress step. So there'd be like rake, there's typically, you'd have rake and compress phases. You could rake the leaves at the bottom and you compress that information and as you pass it up, back up the call stack. Now that would require not having a bunch of call frames. So you'd have to, somehow move down to a child without adding additional stuff to the stack frame, which would require, an iterative kind of approach, but still knowing where to go back to. Realistically, I think you are going to end up doing linear space complexity. All right, so how do we do this? The simplest solution is actually not the most straightforward, but that's the one I'm going to go through today. Instead of thinking through, okay, my first attempt, I thought about if I made some kind of custom structure, like if it's C++, use a class, because then you only have to remember one type of way of declaring structures. So like uh, properties, I did something like this, and then it had like the low and the high, and then like a like a is BST Boolean, something like that, where the children would then pass up the bounds of their low and high like windows that they found, and then the parent would compare that against their node and see if like, so for example, this three would return low and high with 3 to 4. This 4 would then know that its bounds were 3 and 6 below it, and then it would turn that to 5, and 5 would say, oh, the lower bound of my right child is 3. I know I'm not a binary search tree. That's kind of the intuitive approach, and maybe that would work, but the most clever solution is actually like, let me talk about that. It involves a single bound. You only track one bound, and then you'd recurse on that one side first. So if you wanted to say track the left bound with a variable, and then you continually recurse on the right, then you only need the one. So it'd be like int, I don't know, low or something. And you'd initialize it to, I'm going to show you a library function that I think is important enough to memorize. It's called numeric limits. And you can give it, your data type, and then you can set like a min, or you could do something like infinity. I don't think it does negative infinity, but you put a minus sign, boom, you're in business. However, it's if you don't read the documentation, you're gonna get a silent error if you use it with an integer type. It's gonna run fine, but infinity for integers resolves to 0. That is not what you want. You need to use a floating point like a double or a float. So float or double, something like that. And actually, this problem has some edge cases where they'll have the root be the 32-bit integer minimums and maximum, which is like somewhere in the 2 billion range. If you ever played RuneScape, it's the gold stack limit. So, fun fact, that's how you remember. So you need this infinity, quote unquote, to be like the first time you do infinite, if you have just a float, the first time you compare it against, say, an integer, maybe it'll lose. There's something weird with the type conversion, the implicit type conversion that happens. So I found that actually for this problem, due to the edge cases being at the 32-bit integer limits, you actually need to do a double for this to work. You need to denote your infinity with a double. And that's really deceptive. And that's just like, that would be so unfair to ask someone that in an interview. Or if it is, it's like, you better be going for a high-end embedded role or something where they're paying you boku bucks to catch this kind of edge case on the fly during an interview without having to like, you could get through it just fine if you like sit there and debug and think about it and spend some time and maybe read some documentation. But in an interview, no way, no way, no freaking way. Anyway, so we've got our variable that we're tracking now, initialized to minus infinity. So as always, it's both recursive and the input is a pointer. So you want to do something with that. With recursive, you always need a base case. With pointer, you always want to check if it's null. And in this case, we're going to do both at the same time because that's null. We're going to make null our base case. So if what? If the root is null. What do we want to do? Well, by default, since we're using the children results in our higher up definitions, say the root is null. Well, we're gonna, for the sake of this, we're gonna say that that's true. That is a valid binary search tree if the root is null. Technically, I think it's let's see, does it have to be strictly? Yeah, it just says, it doesn't say less than or equal to, it says less than. To be a valid binary search tree, the children have to be on the left have to be strictly lesser, and the children on the right have to be strictly greater, which is a key point to make, because when you're dealing with a null parent, this is actually, it's going to be an exception, and this will pass the test cases, but this is technically an exception where, you know, if you have a null parent and you have null children, they're equivalent, so it's not, there's no strictly relationship there. That is an exception. Not in an error sense, but it's an exception to the rule, to the pattern, to the requirement. All right, so what do we do next? Since we're tracking the output with this variable on the left side, that means we should check that first so that later we can compare, and then we'll do the right side last because we're not tracking that, if that makes sense. So for example, if we were tracking positive and we always did, you know, mins, then we would do the right side first because we would not be tracking the left side. But I think it's a little easier to conceptualize if you're going left to right, unless you, I don't know, unless Arabic is your native language or Japanese and you read right to left. Do they read right to left in Arabic? If your language is right to left, this would be less intuitive for you, but this is English, so we go left to right. All right, so first we need to do the left child. So uh, if if our left child returns negative, then we're also going to return negative. It's an early break. So if not is valid, binary search tree, root left. And we want to continue if it's true. So that's why I have this if else condition instead of just like return is valid BST. Anyway, so we check our left child first. And if that returns true, then we keep going. What do we do next? So we need to do a comparison. We're going to be comparing, let's see, these values. So when it's a tree node, these values are integers, meaning we're going to be doing a max or a max comparison of an integer and a double. There's a couple ways to do this. I'm going to do a macro because I think it's a little nicer to show off, because you're going to get an error if you try and just use a regular max call. It's not defined for different data types. You need to have the same data type or use like just like a hand rolled comparison. So you're going to do something like pound define, or you could also do a custom function too, but I don't know. It's a max, and it takes two arguments, a and b, and you're going to as a, if a is greater than or equal to, it doesn't matter. It could be strictly, it doesn't matter. If they're equal, it makes no difference. B, then we return a, else b. And if you've ever had any formal training or read anything on macros whatsoever, in your use case, in your usage here, always put parentheses around each of the variables each time you use them, because macros do dumb replacement, and you're going to have some very unexpected results if you have anything like compound or complex in there. So I think it would look bad. Your interviewer will judge you if you do not have parentheses around all of your variables in your macros. So that means low is now equal to max of low or root val. That was much ado. You could also do something like low equals, you basically hand roll it. So if low is greater than root val, low else high, or sorry, a root val. That would also work. That's pretty much the same thing. Anyway, let's keep one of them. And then we keep going. So EF. Actually, at this point, we can just, we set it. We need to compare. So EF. No. Before or after, let's compare now, actually. If low is greater than or equal to, because of our strictly requirement, strictly different, equal to our root val, return false. And then we set low. We could do it before or after. I actually don't think it really makes a difference if you do it before or after, or does it? If low is greater, so if root val is greater, yeah, I don't think it'll make any difference, because if this is bigger, then you set this to that, and then you're gonna see that low is equal, so that'll return false. And if low is greater, then you're not going to adjust it at all. So that's fine. We have our update step. And then finally, we return, we're going to explore the right child. Is val root right. We could do a similar syntax as this. It doesn't matter. Realistically, okay, so we did our exploring of the left child. We did our work, since it's recursive, and we're doing basically, this is basically in order traversal, I think, because we're exploring, yeah, we're exploring the left child, checking all those, making sure they're all binary search trees. We do our work in the middle where we update and we do our comparison, and then we explore the right. And we're not tracking the right, so we don't have any work or variables, and I think that'll do it. So let's see. I already talked about time and space. I'll just write those out and then not talk about them as much. Actually, it's okay. We'll justify it with actual concrete code. That's constant. This is constant because that happens initially. Maybe you'd make a constructor for that or something. This explore to left. This just goes down. This is kind of linear. You only hit everything once on the left. This is constant work because it's a constant number of bits. Remember, runtime is actually linear on the number of bits, but when the number of bits are constant, then it becomes constant work. And then we recurse on the right, and that also hit all of the right children just once. So it is O of V plus E time and O of V sub base. And actually, since it's a tree, these two are pretty much equal, so you can drop one of them. And yeah, and the space is for the stack number of stack frames, the call stack. So yeah, O of E, it's O of E time and space. And let's do an example. I'm gonna do this one, I guess, since it's a little crazier. Okay. I don't know how I'd write this out, I guess. Maybe, well, I'm gonna for sure list it. So low equals minus inf to start out. Okay. And then we'll have I'm gonna have this just like a stack to keep track of what variable we're on and whether we've gone left or right. So we start off at 5. And then the root is not null, we go left. So now we're at 1. 1, we check its left and right children. So first we check the left child, that returns true. And then we do work. Well, 1 is we're gonna adjust our minus infinity to 1. Because this is gonna return false at first. So that's not gonna trigger. So then we adjust minus infinity versus 1, that goes to 1. And then we recurse right. Right on from 1 is null, so that's going to return true. And then we go back to 5. 5, that's going to return, so it's, since 1, we got that far, we had not returned false. 1, that's going to return true, so then we return true back up to 5. So now 5, we're going to go to the right. And from 4, we're going to go, 4 is not null, so we go left. So now we're at 3. Same thing, 3 is going to check the left child. That's going to return true. So we don't hit this. So now we do our work on this node. Low is currently 1, so we're going to update that. Take the max of low. Wait, so if low is greater than root or value, if 1 is greater than 3, it is not. So then we update it. Low is now 3. Okay, and then we recurse right, which is null. That's going to turn true. And since that's true, we return true back to 4. So now for 4, back at 4, and then we recurse right, 6. So we're at the 6. Left, that's true. We do work. Okay, we're at 6. We already checked that. That's the return true. So then if low is 3, is greater than or equal to 6, it is not. But now we're going to update it. So now it's going to be equal to 6. And then, yeah, okay, so then it's updated. And then we recurse right. Well, right from 6 is null, so we're going to return true back to 4. And then, so since 4 got true, that's going to return true back to 5. And then 5 would, that's incorrect. I don't think this is going to be correct. What did I mess up? All right, if low is greater than our root value, so 1s, that's fine. Oh, you know what? I think when we hit 5, let me back a little bit. So suppose we're at 5 and the min is back to 1. All right, I'm going backwards in the example here. I forgot to update this low. So we come back from the 1, that returns true. 5, we're going to update this low to 5. And that's before we recurse right. So by the time we get to this 4, that means, okay, so 4, we recurse left. This is 3, so we're not going to update our low. And then right child is going to return true, so 3 is going to return back to 4. And then when we do work on 4, we see that this low is 5. Low is 5 versus the value is 4. And so we're going to return false. And that means that 5 is going to return false because it got that from its right child. And then we break return x. Okay, so that is correct. And then, all right, so since I got lost there, I'll do the first example here. All right, minus infinity. Hopefully we'll make this a little quicker. All right, start off at 2. 2 is not null, we go left. 1 is not null, we go left. And then we do work on that, so this is going to become 1. And then we go right. That's true, so then we return true back from 1. So now we're back up at 2. And then we do work on 2. So 2, we're going to update our min to 2. Because there was 1, that didn't happen, so then we update it. And then we go right. Now we're at 3. 3 is, we're going to go left first, that's true. And then we're going to update it, so then we're going to compare 2 versus 3. That's not going to trigger. And then we update, it's now 3, and then it's null, the right is going to return true, and then 3 is going to return true back to 2, and then, but we got up to 2, and then so that's going to return true out. So yeah, okay, there's our example. Let's go ahead and run it, and then hopefully call it a night. Oh no, syntax error. Oh no. Root declared, yeah, root val. Use of undeclared, oh, root, as opposed to root. Cool, all right, and then submit. Boom. All right, check, and good night, ladies and gentlemen.